Hey everyone, let's jump right into this explainer and uncover how scientists conquer the totally chaotic world of macromolecules. We're talking about size exclusion chromatography, or SEC for short. If you've ever wondered how on earth researchers manage to take a complex biological sample or some messy industrial synthetic mixture and neatly sort out the massive molecules from the tiny ones, well, you're in the right place. Today, we're going to break down the fascinating mechanics of this technique, but more importantly, we're going to zoom right in on its specific domains of application. Let's get into it. Here is a quick roadmap for our explainer today. First, we'll welcome ourselves to SE's domain, then look at the unique strengths of the technique, dive into analyzing complex polymers, talk about calibrating the columns, and finally, choosing the right gel. All right, part one. Welcome to SEC's domain. So, size exclusion chromatography, which, by the way, you might also hear called gel filtration if you're using an aqueous mobile phase, or gel permeation with an organic one, is actually kind of an outlier in the chromatography world. Why? Because instead of relying on chemical affinity or electrical charge, the migration velocity of a component depends entirely on its physical size, and, indirectly, its molecular mass. There's this great analogy that perfectly captures the core principle here. Think of the molecules like vehicles, and the pores inside our chromatography column as a city's traffic network. The quote says, "Trucks using the bypass around the city can move faster than cars using the smallest streets." It's brilliant. Inside the column, the stationary phase is packed with porous beads. The small molecules, the little cars, wander into all these tiny pores. They're taking detours, so their journey takes way longer. But the massive macromolecules, the giant trucks, they physically can't fit into the pores. So they just wash straight down the empty spaces between the beads and come out first. It is literally an obstacle course where being gigantic is a massive advantage for your speed. Moving right along to Section 2, the strengths of SEC. Now there are three key advantages, basically superpowers, that make SEC such an irreplaceable tool. First up is the absolute absence of interaction with the stationary phase. In a lot of other chromatography methods, your sample chemically binds to the column, which can really mess with delicate molecules. But here, it's a purely physical sorting process, no chemical reactions at all. Second, you get really rapid dilution. And third, this is a big one. Because there's no chemical binding, you have the potential to recover 100% of all your analytes. Yep, every single thing you put into the column comes out of the column. You aren't leaving any of your precious trace materials stuck behind in the gel. Okay, Section 3, Analyzing Complex Polymers. So what exactly are we sorting here? Well, we are dealing with shear scale. SEC permits the separation of nominal masses ranging from just 200 all the way up to 10 to the 7th Daltons. That is 10 million Daltons. Because of this incredibly massive range, the main domains of application for SEC are analyzing synthetic and natural polymers. We're talking industrial plastics, complex carbohydrates, massive biological proteins. These are gigantic, unwieldy structures that would absolutely choke up other types of analytical columns. But here's the catch. It's not just about their massive weight. We have to deal with the physical reality that a polymer's shape can vary drastically. Imagine two molecules and they both weigh exactly 1 million Daltons, okay? One of them is tightly coiled up, like a dense little pellet. The other is this long, sprawling, unspooled thread. Even though their mass is exactly identical, their physical volume, the actual space they take up in the liquid, is completely different. The string might get tangled up in pores that the little pellet just breezes right past, or vice versa. So you can see how this introduces a pretty major challenge for scientists who are trying to figure out mass purely based on how fast something travels through a column.
Which brings us to Section 4, Calibrating the Columns.
To actually solve this calibration problem, analysts have to meticulously follow exact steps. First, they examine the known calibration curves of various columns. Simple enough. Second, they need to pinpoint a column that gives them a linear, predictable range covering the specific masses they expect to find in their sample. But step three is the absolute golden rule. You must conduct your calibration using the exact same type of polymers that are in their sample. Remember that pellet versus thread issue we just talked about? Yeah, if you calibrate your machine with a tightly coiled globular protein, it is absolutely not going to help you accurately measure a sprawling synthetic polymer string. You have to match apples to apples. And finally, Section 5, Choosing the right gel. Let's look at how this plays out visually. Notice how the gel labeled G2000 has this steep, linear drop-off at a much lower molecular weight than the G3000 gel. That linear slope, that is your sweet spot. It's the selective permeation range where the actual sorting happens predictably.
If your molecule is too big, it hits the exclusion limit, that flat line at the very top, and just washes right through without separating at all. On the flip side, if it's too small, it hits the total permeation volume at the bottom and just clumps together with all the other tiny molecules. Basically, you have to perfectly match your gel's sweet spot to your sample size.
And here is the ultimate cheat sheet showing the exact domains of application for these gels. This translates those curves we just saw into hard data, letting technicians instantly choose between, say, a G2000 or a G4000 gel based on their specific polymer. For example, if you're looking at a globular protein using a G2000 gel, which has 12.5 nanometer pores, the effective range is roughly 5,000 to 100,000 Daltons. But what if you're working with an absolutely massive globular protein, say something up to 7 million Daltons? Well, then you absolutely have to switch to the G4000 gel because it has much larger 45 nanometer pores. This perfectly proves our main point today. In SEC, the physical architecture of your tools has to perfectly mirror the physical reality of your molecules. To wrap up our explainer today, I want to leave you with a thought about where all this is heading. Size exclusion chromatography allows us to sort and analyze materials up to 10 million Daltons without degrading them, which easily makes it the undisputed heavyweight champion of modern chemical analysis. But as materials science keeps pushing boundaries and we start engineering even more massive and complex synthetic polymers, what radical new separation technologies are we going to need to invent when even SEC finally reaches its limits? It's something to think about. Thanks so much for joining me for this explainer, and keep exploring the fascinating world of analytical chemistry.